So I think we can start. Let me make a couple of announcements before. And let me first thank all the speakers up to now. That has been everything so nice and so interesting. And I'm sure that until tomorrow will be really, really interesting. I think we have really a nice program. And so the announcement two. One is that tomorrow we have a speaker missing, is Ansgar Stelland. His talk was supposed to be at 9, so I will just shift every talk a half an hour in advance, maintaining the same sequence of speakers. So we start at 9, we will be done by 12. Okay, so that's the first announcement. The second one, it was already said, announced, in the sense there will be the Scandinavian Journal of Statistics that will have a special issue on the workshop. So we have essentially this scheme. There will be time until the 31st of October to make submissions for the special issue. There is no slot for the special issue on the website of the Scandinavian Journal of Statistics, but essentially in the accompanying letter you would have to mention that the paper is within. The aim is the special issue for the workshop. Anyway, after the workshop is finished, I will put more information on the website. So please control it even after the conference. I think I will also put the pictures that we have, and we registered every talk, so I think I will put the sessions for every one of us and everyone that is interested to have a look at the workshop. So now our first speaker is Stathis Paparodidis from University of Cyprus.
So thank you, Manuel. Thank you very much for the invitation. And thank you for being here in this hard time of the day. So this will be a talk actually related more to the related topics of this workshop. It's not goodness of fit, it's not change point, but it's an approach how to make statistical inference in a case where you have a high-dimensional vector autoregressive model. And this is joint work, still ongoing joint work with Jonas Krampe and Jens-Peter Kreis. Okay, so here's an outline. I will somehow describe the high-dimensional setup we are going to consider. Then I will introduce or define so-called disparsified estimators of vector autoregressive parameters. We'll discuss this in great detail. Then I will tell you something about how to do bootstrapping in this sparse vector autoregressive setting. And then I'll give you an application in testing where bootstrap is important in the context of testing hypothesis in this high-dimensional setting. And I present you some numerical results. Okay, so we're dealing with a p-dimensional vector autoregressive process. So you see xt depends on its past, d past values. This is p-dimensional vector. And epsilon t is in white noise. Actually, it is an IID, innovation process with mean 0 and covariance matrix sigma epsilon, which is positive definite. We also assume that this condition is here satisfied. Actually, this tells you that this process is causal. So you can express xt as an infinite series of past innovations. This is actually a very comfortable assumption because this allows you to do many calculations. Okay, so we're in the stationary setting. Now, suppose you have a time series x1, x2, xn stemming from such a process, and you want to infer properties of the underlying vector autoregressive process. Now, if you look at the number of parameters you have to estimate in this p-dimensional process, then you have d times p square parameters regarding the coefficient matrices A, And then you have P times P1 divided by 2 because of symmetry of the parameters in the covariance matrix of the innovation sigma epsilon. So this means the number of parameters in such a model is of the order of P squared. Now, the classical setting is the one where you assume that the total number of parameters Q is much smaller than n, or at least it's fixed. So when you increase, you let n go to infinity at some point, n becomes large enough. And then you can do inference on this type of models. This is a well-investigated area. I mean, there are amounts of paper on this. There are even books where you can find many things about this type of processes. I just mentioned here 3 of them, but there are some more around. The interesting and important case, I think, in some applications is the one where this number Q is much greater than n. Let me give you an example. I'm not an economist, but as far as I know, one interesting question for economists is the question whether the stock market affects the labor market. Okay? And there are many papers about this problem in the econometric literature. I mentioned one more recent. This is by Pharma, 2015. And what he's doing is actually he uses a bivariate time series. So actually he uses one time series, the S&P 500 index, as a time series describing the stock market, and the unemployment rate as a time series describing the labor market. And he do a bivariate time series analysis in order to decide if this hypothesis is correct or not. Of course, you can say that you reduce the problem to a bivariate one. Why you should do this? And you lose information, of course, because you exclude many other time series which describe the labor and the stock market. So, but what if you do the other thing? Just take all information you have in your data set. Suppose you use the entire set of time series of the Federal Reserve economic data. These are something 124 time series, and you have observations, quarterly observations, so n equals 126. Now, even if you want to fit a vector autoregressive model of order 1 to this type of times or to this type of data, of course, you end up that you have to estimate something like 23,000 parameters or more, okay? And if you want to test this hypothesis, so you have to test that 150 coefficients in this vector autoregressive, in this coefficient matrix of the vector autoregressive model of order 1 equals 0. And of course, you see that without any further restrictions or assumptions, it is not possible to do at least inference in this setup. So the case we consider is the following. This is one way to do inference for this kind of problems. Is the case where you have a sparse vector autoregressive model. Sparse means actually that Q is much larger than n, but the number of non-zero parameters in this system is small. Okay, this is the basic philosophical assumption we are doing. Before proceeding with this, let me just fix some notation I'm going to use in the following. So I will avoid as much as possible technicalities. So the index 0 here describes just the number of non-zero elements of a matrix C. Okay, so you have the one and the infinite norm. This is you look just at the columns of this matrix. You take the sum of the absolute value of the coefficients, and then you take the maximum of this, and you do the same for the rows. Okay, so this refers to the rows, and this refers to the columns of the matrix. And then what I'm doing, I'm assuming the following, that D equals 1. So the order of the process equals 1. This does not change anything in what I'm going to say. The paper is written for the general case, but this will make the notation very, very, very difficult. Okay? So what we do, we allow also for the dimension B of the vector, P of the vector, to increase to infinity. And there's an essential difference here compared to the regression setup. When you increase the number of explanatory variables you have in a regression model, then you increase the number of parameters you don't know, at least in the vector beta, by 1. When you do this in a time series context, when you increase the dimension by 1, then you increase the number of parameters in this D equals 1 case by 2p plus 1. So the number of, you have much more unknown parameters when you allow the dimension of the process to increase with n. Okay, so K1 max denotes the maximum of the non-zero coefficients in the rows and in the columns of the matrix A. So we are in the case D equals 1, okay? So K2 is the number of non-zero elements in the matrix of the innovations, and K max is just the product of the two, okay? Now, you can write the vector autoregressive model of order 1. If you pick up the tjth element of this vector, you can write the equation describing the dependence of this xtj in the following way. So you see these are the coefficients a, j, l, which are on the same row. Okay, and then you have xt minus 1 l, and then you use the vector xt minus 1 to describe xtj, plus the innovation epsilon tj. You can put this, of course, in a like regression setup, where you define the vector xjn to be the vector x2, x3, xnj of the jth component. You have a kind of design matrix here. This is just the matrix giving you the lag 1 observations. Okay, and then you have the epsilon j n. And then, of course, you can think of this as a regression problem. Okay, and then, of course, because you are now in the high dimensional case, there are some ways you can estimate this unknown parameter vector aj. This is a vector now, so you can work on this vector. And one way to do this is just what we talked yesterday a little bit about. This is Lasso estimator. So this is a penalized least squares estimator where you penalize actually by this lambda x parameter using the L1 norm. Okay, this has been done in the literature by Michailidis. This is a paper in Annals of Statistics which has investigated the properties of this type of estimator. There's another paper by Koch and Carrot which is actually more interesting because they look at the so-called adaptive lasso. The adaptive lasso is actually the difference is that you change the weights, so the restrictions you're putting on the coefficients, and you put the penalty according to the coefficients. This means when the coefficients are small, you put a larger penalty. When the coefficients are large, you put a smaller penalty. This is the adaptive lasso, and this has been investigated also in this type of models by Koch and Carrot, and this is by Richard Davis and his co-authors, similar approach based on penalized maximum likelihood. So you can estimate the columns of this matrix in the way I've described before, okay? And then they have shown that if you have Gaussian innovations, if you have a Gaussian process, then you can say something about the rate of these coefficients, and this is K1 max. So remember, K1 max is just the number of non-zero coefficients, and square root log p divided by square root n. In fact, you see this is what you have to pay because of this high dimensionality of the problem. Okay, but then you can do it in a different way. They are so-called regularized Euro-Walker estimators. I mean, people working in time series, and especially for vector autoregressive models or for autoregressive models in finite dimensional case, they know that Euro-Walker estimators are nice estimators for several reasons. So there's an approach to extend this type of estimators by Han and al. In this context of high dimensional data, vector autoregressive models. I mean, it looks somehow strange, but the idea is you use the basic equation of Euro-Walker equations, okay, and then just you penalize again. So you use the L1 norm, gamma 0 tilde and gamma 1 tilde as just the lag 0 and the lag 1 autocovariance matrix estimators. And they have also shown that if you have Gaussian innovations, actually all results existing in the literature for this type of models regarding rates, they are for Gaussian or at least for sub-Gaussian models. Okay, so they get the same rate, but now you see, you look at here you look at the rows of the matrix, here you look at the columns of the matrix A. Okay. So, but despite this type of rates or consistency properties, the limiting distribution of such estimators is unknown in the context of time series. And even if you look at the IID case, I think yesterday you had a comment on that. Knight and Fu in an Annals of Statistics paper derived this distribution for in the context of IID regression models under certain simplifying assumptions, and this distribution is non-standard. Okay, and there's some discussion about this, especially by Chatterjee and Lahiri, who looked at the type of bootstrap procedure for regression models. They show that if you go in the classical way and do a parametric bootstrap for this type of models in the IID regression case, then this fails, so they propose an alternative approach. So I think that it seems that this type of estimators are useful for some things, but they don't seem to be useful if you want to do inference for this type of models. So, and this is why I'm going to move a little bit forward and introduce a different type of estimators, which are called disparsified estimators or debiased estimators. And I'll try to explain what actually they're doing. Of course, the advantage, as you will see, is that they have a regular limiting distribution. So this is a normal distribution, okay? And this enables you to use this type of estimators to do inference. We'll see how we'll do this in the following. Okay, so what is the bias? Okay, these are not new estimators, especially in the IID context. There are many papers discussing this. I just mentioned the one by Zhang and Zhang. This has been introduced, this type of estimators, and there's another statistics paper by Gier, Bullman, and so on, looking at the properties of this estimator, and Bullman and Zhang, they did also some bootstrap-based procedure using this type of estimators. In the time series context, things are much more involved. I will explain this in a couple of minutes. There are some approaches, but actually in a very restrictive setting, first of all for Gaussian time series, and then for very specific situations. So we are going to define this type of estimators, and this is what I'm going to do next. So look again at the same equation we had before. So the xtj, so how do you explain the element, so the component j of the vector xt, okay? Now if you go back to the standard case, where p is less than n, much less than n, and you look at the least squares, as the classical least squares estimator of AJL, okay, I just wrote it here, AJS, you can express this least squares estimator in the classical setting in the following way. So this is actually the empirical covariance between these random variables vt minus 1s xtj divided by vt minus 1s xt minus 1s, where this vt are now the residuals you get when you project xt minus 1s on all other remaining variables of lag 1, okay? So this is an alternative way to express the least squares estimator. So this is what I'm saying, vt1 is xt minus 1s minus this part here, where this part, the coefficients here are just the coefficients you get when you project xt minus 1 on this, on the remaining variables of leg 1. So you can write this estimator in the following way. So in the classical setup, you can write it in the standard setup in the following way. This is the unit matrix when you delete the S row. And then you have here the sample covariance matrix, okay, at leg 0. So this is what you can estimate. And then when you do this exercise here, you get the coefficient matrix beta unit here, and then you can just calculate the residuals. Of course, if you are in the high dimensional case, you cannot do this in this way, because this Vt minus 1 is identical to 0, okay? So xt minus 1s is in the space bound by the other variables. So, what you can do is the following. You can do the same idea. You can use the same idea, but just replace now the estimates beta tilde by appropriate estimates beta hat here, where the estimates beta hat are now obtained. So you see, in fact, it's the same formula, but with one main difference. This gamma hat here is not the sample covariance matrix as before, is regularized and consistent estimator of this gamma matrix. So how does this look like? I will describe this in a couple of minutes, okay? So this is the basic idea. Once you have this, of course, you can plug in the numerator and denominator of zeta t minus 1s. You get this type of estimator. Now, if you substitute in this estimator xt minus j, you can write it in this way. So you see aj as tilde is the parameter you want to estimate, plus this term, plus this one. So this one you can understand as the bias you introduce in doing this type of estimation. But then you see you can estimate this bias, because if you have some estimators of AJL, you can plug them in and you can get an estimator of AJL. So and this is what you do here. So you see you have an estimator, a regularized estimator of these coefficients, and then you get this estimator here. And correcting the initial estimator for the bias. And this estimator is called D-bias or D-sparse. It is not sparse anymore, of course, and it's called D-bias estimator also because you correct for this bias. Okay? So, when you look at the asymptotic properties of this type of estimator, two things are important. Okay, I'm not going into the details, but I'm going to explain you the basic ideas. Now, the first question is how to estimate gamma 0 in a sparse way, or say in this context of a sparse autoregressive model. Okay, there's a direct approach. You can say, okay, I can estimate gamma 0 by estimating gamma and putting some threshold, so I can get some threshold estimator of gamma 0. But this is not the correct approach, because if you are in the time series context, you can have a sparse matrix A and a sparse matrix sigma, but not a sparse matrix gamma 0. Okay, it's difficult to control the sparsity of this matrix gamma 0. As I said, it's easy to construct an example where you get a non-sparse estimator of a non-sparse gamma 0. Okay, so the basic idea here is the following. In this time series setting of vector autoregressive models, you can express gamma 0 as this series where you see you have AJ and the A transpose in the power of J and sigma epsilon. So the idea is just to use the sparse estimators you have for the matrix AJ, for the matrix A, plug them in, and the sparse estimators you get for the matrix sigma epsilon, plug them in, then you get an estimator for gamma 0. Okay, so this is the basic way. Because actually what we want to do is to impose sparse assumptions on A and sigma, okay, not on gamma 0, because this you cannot control. Okay? So, now, if you look at this, and if you look at the infinite norm of the difference of such an estimator, or because this is a symmetric matrix, so this is the same as the L1 difference. If you want this to go to 0, then you have to control the difference between A and A hat and A. Then you have to control the difference between A transpose and A, okay, the estimator, which is just the infinite norm of A hat minus A, and then the L1 norm of sigma epsilon hat, okay? So this means you need to have an estimator of A which somehow controls the error you are doing in the rows and in the columns of the matrix A, okay? So this is important to get consistency, at least for the matrix A. So now regarding the second point, regarding the asymptotic distribution, so you can decompose the square root n, this estimator minus AJS in two parts. So this part you can think it contributes to the asymptotic distribution, and this part you can think because it depends on the difference between the estimator AJL and the parameter AJL, this probably will be asymptotically negligible. So in fact, you can verify this, okay? If you put some assumptions on the estimators you are using, you can verify this. Okay, I don't want to discuss them in great detail, but the basic idea here is, okay, you allow the number of non-zero parameters to go to infinity, okay? You require that the matrix A you use in your estimator satisfies this condition. But you remember, as we told before, you can use the adaptive lasso estimator and the penalized Eurovoco estimator, so that gives you these rates. So you need an appropriate rate also for the estimation of the covariant matrix of the innovations, and you need some conditions about the moments of the innovations. So the question is, how can you construct such an estimator which satisfies these conditions, okay? And we are doing this in the following way. What you do is actually you use an estimator, a basic estimator, and then you threshold this estimator using the support of two other estimators. The first estimator works in the rows, and the other estimator works in the columns of the matrix A. So this is the basic idea, okay? So actually we put here the adaptive lasso estimator, This is the one we're using here too. And then you use the penalized Euro-Walker estimator here. Okay, AN is, of course, a thresholding parameter you have to select. In this context, you cannot avoid this. Okay, but this behaves like square root log p divided by n. And, okay, this is what I said before. Then you can show that you get these rates you want. And for the covariance matrix, I think I can speed this somehow up. So you get the residuals. When you have the estimates of A, you get the residuals. You can estimate the covariance matrix of the residuals, but then, of course, you do a thresholding again. So you push to 0 coefficients which are small enough. Small enough means smaller than the threshold parameter beta n. Okay, and then you can show this actually goes back to Big and Levina, so you can use these ideas here to prove that this actually gives you the order you want. Okay, so under these assumptions, you can show that this disparsified estimator has a limiting normal distribution of mean 0 and the variance tau square. Two things are here important I want to mention. So you see the limiting variance, or the variance of the limiting distribution depends only on the second order structure of the process. This means on sigma and on gamma 0 only. Okay, so this is important for the bootstrap we are going to discuss after that. And then the other thing is I have put here the limiting distribution for one element of this matrix. But if you look at any number of such elements of this matrix and the estimators, and this is important, these are not uncorrelated asymptotically. Okay, so there are correlation between them, which is not vanishing. Okay, so now let's just go to the bootstrap, because the idea is we want to use this type of estimators to do inference. Okay, especially we want to use this type of estimators to test hypotheses about the parameters of the matrix A. Okay, so the basic idea, of course, is straightforward, more or less. What you do is actually you try to generate a new pseudo time series x1, x2, xn star, which somehow imitates these properties of the underlying process, especially the sparsity properties of the underlying process. Okay, this is the basic idea. And then once you have this pseudo time series x1, x2, xn star, of course you can calculate, you can do the same thing you have done before to get the disparsified estimators, but now using this new pseudo time series, and then you can hope that your procedure is good enough so that you can approximate the distribution of this parameter by the corresponding distribution of the bootstrap parameter. So this is the way it works. Okay, so you use, okay, I put it here in a more general way, but they could be exactly the same estimate as the one you have before. Okay, so there's no reason they should be different, but at least for the sake of generality, you can choose any other estimator you want. Okay, satisfying. So then the bootstrap algorithm is this. Okay, this is important to mention. So you see in the first step, you generate the epsilon from the Gaussian normal distribution, for the Gaussian distribution, okay, with estimated covariance matrix sigma epsilon. So this is not restrictive, because if you're interested in the distribution of the disparsified estimators, so the only part of the distribution of the innovations which affect the distribution of the disparsified estimators is the variance, the covariance matrix, sigma, okay, not the distribution itself. So, and then, of course, this is standard procedure. So you generate the xt stars. So once you have them, you calculate the disparsified estimator using these x stars, and then, of course, you can use this type of quantity here to approximate this type of quantity. Okay, so. Of course, it's important to use sparse estimators because you want to imitate the sparsity properties of the underlying process. And the bootstrap approach is not limited to Gaussian distributions, of course. You use the Gaussian distribution to generate the pseudo innovations epsilon t star, okay, as I said before. Now, you can put the same assumptions as before, okay, more or less, and then you can prove actually this theorem which tells you that if n goes to infinity, then this bootstrap procedure works. So this is Mellow's metric, which means actually that the distance between so they converge to the same limiting distribution, to the same Gaussian distribution, and you can also get consistent estimators of the second moment of this estimate. Okay, so let me look at an application in the context of testing, because this is interesting, at least in my point of view. So look at the following problem. So you have the matrix A I discussed before, and suppose that G is a subset of indices from 1 to P. So I runs from 1 to P, and J runs from 1 to P. Okay, and then you want to test that all coefficients belonging to this set G, they are equal to 0. Okay, and the alternative hypothesis is that there are at least one coefficient in this set which is not equal to 0. Now, you can use, of course, you can think of different test statistics you can use, but you should keep in mind that this G can be very large. Okay, so if you try to construct a type of world statistics with hoping for limiting chi-square distribution, the problem is, we have tried this, the problem is that you have to estimate the variance covariance matrix of these estimators, and when G is large, this becomes very unstable. Okay, so you get problems. So one approach we found very useful is this one. So what you do is actually you take the disparsified estimator, you inflate this by square root n, and you divide by the standard deviation. Okay? So, and then you look at the maximum of this, say, studentized test statistic, the absolute value of the studentized test statistic in the set G. Okay? So, and if this is larger than a threshold, then you reject the null hypothesis. Okay? So you can apply the bootstrap to do this test, because you see it's difficult to get to the distribution to this Tn, because you have here the maximum of a dependent number of Gaussian, at least in the limit Gaussian random variables. Okay, so you can apply the bootstrap, but the only thing you have to take care of is that when you apply the bootstrap, you want to generate x1, x2, xn star, satisfying the null hypothesis, because you want to approximate the test statistic you are interested in, the distribution of it under the null hypothesis. Okay, so you have to impose the conditions you are, the hypothesis you are doing. You have to impose it in the parameter vector A, J, S. So this could be a small problem, but we can discuss this after if you want. So of course you can then define T and star in the straightforward way, and then you can use the percentage points of this T and star just to do the test. So you reject if this is larger than the upper A percent point, alpha percentage point of this distribution. So let me give you some 2 minutes. How many? 5? No, because I started this. Okay. Okay, I have to speed up. Okay. We look at 20, 100, and 200 dimensional process. Okay. And then we have a matrix A. I can show you how this matrix looks like. So this is a case 100 by 100. So we have this particular structure chosen because this is one has been used before by people. So there's a cluster structure here. So blue is actually a large parameter, and red is a negative large parameter. Okay. The cluster structure is not important. You can reshuffle these coefficients, and you get something like this. So this is the A matrix. Okay. And what we have looked at is the following. Case 1 is the case where this set G has 400 members. Okay, so you want to test that 400 of these coefficients are equal to 0. And case 2 is the case where you have 100 coefficients in this set. Okay. Okay, I don't have time. I can show you some pictures. Look at this one here, which is with bias correction. So lambda max, this is just the maximum eigenvalue of the metric, the absolute value of the absolute value of the eigenvalues, the largest one of the matrix A. This is important because the closer you get to 1, the instationary will be the process. Okay. So we have 2 sample sizes, 128 and 200. So here is the 20-dimensional process, the 100-dimensional process, and 200-dimensional process. It looks very nice, really. It looks very nice. It looks amazingly nice. The same, if you look at the power, okay, I have to say something about the power. So what we did, we changed only one element in this set, which is 0. We changed only one element randomly and put it to the value of 0.3. Okay? So, and this is the power you get on the H1. So test seems to have a very, very nice power. Let me come back to this example I started at the beginning, okay? So this is the setup you have. And then if you want to test this hypothesis that the financial sector does not affect the, or was it the other way around? Was it? Okay, was it? Yes, it was this way around. So the financial sector does not affect the labor sector. So if you try to do this, to translate this hypothesis in the context of this type of model, then what you have to do is to test that the number of 155 coefficients equal to 0, okay? So we did this by applying the bootstrap procedure I described before. So you see this sparsity of the matrix A. Of course, it depends on the threshold you are choosing, okay, to do the estimation. But if you choose the threshold by 0.9, the thing is that only 2.7% of these coefficients are not equal to 0, okay? So this is the p-value of the test for different values of this thresholding parameter, okay? So this is the 5% threshold, and you see it seems to be independent of how you choose the threshold. You have to reject the null hypothesis. The p-value is very small, which means that that the one market affects the other one. Okay, so thank you very much.
We might have time for one question.
So how about the predictive performance of the estimation?
I don't know.
That's probably the most important question.
I don't know. We haven't done anything regarding prediction.
Okay, then. Thank you. The next speaker is Untitled.
Oh. Okay, so first of all, I would like to join the other speakers in thanking the organizers, so Emanuele and the other people who were involved in the organization of the conference. I think they did a very good job, and we all know that organizing a conference takes a lot of effort and a lot of time, so thank you for all the work that you did. So is the microphone working? Yeah? Okay, so I'm going to talk about Bootstrap in the context of residual distributions. And I want to answer the question whether smoothing is necessary or not in that context. So this bootstrap of the residual distribution is actually very much used in several papers in the context of testing, and in particular in the context of goodness of fit testing. And so in that sense, I think the paper fits into the topic of this conference. So this is joint work with Nathalie Neumeier, and this is the outline. So I'm going to I'm going to start with some literature on this topic, and then I'm going to focus on two particular regression models. The first one is the non-parametric regression model, which is the one which we started with. It's maybe not the logical order, but we started with the non-parametric one, and then later we did the linear model. And then I will show in simulations how the bootstrap that we propose, which is a non-smooth bootstrap, compares with a more classical bootstrap, which is a smooth bootstrap. So this is the model we consider. So we have a classical location model. Y is m of x plus epsilon. So epsilon, the noise, is independent of the covariate. The covariate can be one-dimensional or more dimensional, and the regression function can be parametric, for instance, linear or non-parametric. For the moment, it doesn't matter. all we are assuming is that the residual, not the residual, the error has mean zero, and the distribution, which I'm going to denote by capital F, is completely unknown. So this morning, Winfried mentioned already the paper of Durbin. So Durbin is actually the earliest paper in which this estimation of this error distribution was studied in the linear case. There have been other papers later. And then in the non-parametric case, there are also a couple of papers, but it started naturally later than in the linear case. So this estimation of this error distribution, you might wonder why it is important. Well, actually, this has been used in several contexts in which hypothesis testing for this model is considered. And the first paper was a paper by Wenceslao, Cesar Sanchez-Celiero, and myself, in which we tested the form of the regression function. And we showed actually that testing a parametric form of the regression function is equivalent to testing whether the error distribution is the error distribution under that null hypothesis. And so you can use, in that case, the error distribution to test your goodness of fit problem. Yeah? And then there are a couple of other papers where this same idea is used. So each time you use the error distribution under the null hypothesis and you compare it with the error distribution without using the null hypothesis. So for instance, there are papers on comparing regression curves, on testing independence, on testing for symmetric error distribution, which has been done, among others, by Nathalie and by Holger, testing for multiplicative models, etc. There are actually more than what I'm listing here. So that shows that this error distribution is important in testing problems in regression. Now, as you can imagine, the asymptotic distribution of that estimator, of that empirical distribution function of this error distribution, it has a complicated structure. So it's not a classical Brownian bridge, but it's much more complicated because the estimation of the regression function has an influence on the covariance structure. Yeah? And so for that reason, bootstrap procedures have been used in order to find critical values of these tests. Yeah? So what kind of bootstrap do we use? That's then the next question. And basically, in the literature, there are two approaches. There is a first approach which was used by Cole and Lahiri in 1994 for the linear regression model, and by Nathalie in 2009 for the non-parametric regression model. And the idea in both papers is that you first smooth the empirical distribution function of the residuals, and then you draw bootstrap samples from that smooth empirical distribution function. Yeah, that's the first approach. Nathalie also showed that you can do the opposite. So you can actually first draw bootstrap samples from the non-smoothed empirical distribution function, and then you smooth that obtained bootstrap distribution function. Now, in both approaches, smoothing is used in one way or another. Now, why is smoothing used? Well, actually, for a technical reason. It turned out that the method of proof in these papers requires the bootstrap error distribution to be smooth. So it's really a technical, for technical reasons. Yeah? And so far, it has been an open question as to whether that smoothing is really necessary. Of course, it's useful for the proofs, but is it really necessary? That's the question. And so we will try to answer that question, and we will actually show that smoothing is not necessary. So you can get a consistent residual bootstrap without smoothing, which is, of course, easier because then you don't have to choose a bandwidth parameter. Yeah? And we will do that in the two cases that I mentioned. So first in non-parametric regression with a one-dimensional covariate. And then I will go to the actually easier case where we have multivariate linear regression. Okay, so in non-parametric regression, we consider not a Rye-Watson estimator, but actually you can also use local linear or local polynomial. That's not really essential. With this estimator of M, we construct residuals, and then a crucial ingredient in what we are going to do is this result, which says that the empirical residual process, this one, converges weakly to a certain Gaussian process, which I will denote by W, and that W will show up several times on my following slides. And that Gaussian process has this covariance structure. So you see that the estimation of this regression function shows up in the covariance, because this term here and this one here would not be there if we would know the error. Yeah, it comes from the estimation of the error. Okay, so let's denote by f hat 0n this empirical distribution of the centered residuals. So this 0 means that we are not doing smoothing. Yeah? So the non-smooth residual bootstrap that we are proposing is then explained by these 4 steps. And it's actually, kind of the classical way, I would say, to do bootstrap. So we first draw bootstrap errors from that non-smooth empirical distribution. From there, we construct new responses. With these new responses, we construct a new estimator of the regression function. And with this new bootstrap estimator of the regression function, we obtain new estimated errors in the bootstrap worlds. Yeah? And so all this is done without requiring smoothing. Of course, we need smoothing for estimating the regression function, that's clear, but there is no additional smoothing that comes from the bootstrapping procedure. Okay, so then with this epsilon hat stars, we construct the empirical bootstrap residual process, which is this thing here. Yeah? And so what we would like to show now is that the distribution or the asymptotic behavior of this process here is asymptotically the same as the one of the original process. And that would be nice if we can show that, because then we have a bootstrap procedure that does not involve smoothing. Yeah? So that's our goal. So to show that this is indeed the case, we will look at the difference between what we propose, so the difference between this non-smooth bootstrap and a smooth bootstrap, namely the one that was proposed by Nathalie 10 years ago. Yeah? So from these bootstrap errors, actually you can always write them in that way, with the UI uniform. Why? Because they were drawn from this f hat 0n. And so you can always write them as a quantile of that f hat 0n. Then this UI, we use them to construct smooth errors. So now I'm at S, and the S comes from the smoothing. And these smooth errors are quantiles of this smoothed empirical distribution, which is this thing here. So I smooth my empirical distribution with a certain kernel L and with a certain bandwidth S. Yeah? Okay, and now the next step is with these errors, these smooth errors, I obtain now smooth bootstrap residuals. In the same way as I did it on the previous slides here. Here I did it without smoothing, and now I replace this thing here by the smoothed quantity. And that leads to this thing here. Yeah? Okay, so what we are interested in is the asymptotics of this process. And I'm going to decompose that process in 3 terms by adding and subtracting the empirical of these smoothed bootstrap residuals. That's this term here. And also by adding and subtracting the smoothed empirical distribution. So the f hat Sn, which I defined here. Yeah? So in this way, I create 3 terms, which I call T1, T2, T3. And what we showed is that T1 and T3 are negligible. So it means that smoothing is not necessary in the real world and also in the bootstrap world. These things here and these things here, they go to 0. Yeah? And so we are left with the middle term. And you might think that the middle term is exactly what Nathalie did in her 2009 paper, but it's actually not exactly the same. So there is still some work to be done. And the difference is actually that what you do usually in the smooth residual bootstrap is you create these bootstrap residuals, which is still something else, because now we also estimate the regression function by using smooth bootstrap data. So we smooth both here for the regression function and in the errors. And then you really do what Nathalie did in her 2009 paper. So what we showed is that this term T2 is asymptotically equivalent to the smooth bootstrap residual process that is built with these residuals. Yeah? So these are the ingredients. So there are different steps in the proofs, but that's more or less the sketch of the proof. And so at the end, we use then the result of Nathalie, who said that this process, the smooth process, has the same limiting Gaussian process as the original empirical residual process. And so they both converge to this W, which I defined before. Yeah? And so now we come to the conclusion, namely that without introducing smoothing in the bootstrap procedure, we get exactly the same limit asymptotically as when you use the smooth bootstrap. And so in particular, we have consistency of this non-smooth bootstrap. Yeah? So that was our first main result for the case of non-parametric regression. And as I mentioned before, this can now be used for doing all kinds of hypothesis testing in the context of regression, or it can also be used to obtain, for instance, confidence bands for the error distribution. And I will show you in a minute in the simulations how this performs. Okay, now I will quickly show you how things work in the linear regression case, but the idea is actually very similar. Yeah? So let us quickly go through the slides, but I'm not going to give all the details because they are really very similar to the non-parametric case. So now we have this linear model, and to be a bit different from the previous case, we consider here a fixed design. Yeah? So the x's are non-random. We consider the least squares estimator, and these are then our residuals. And there is then the paper by, or not a paper, it's the book by Hirakul in 2002, who contains this result. So the empirical process, the empirical residual process converges weakly to a zero mean Gaussian process with this covariance structure. And again, you see that the estimation of the beta makes this covariance more complicated, because normally For the empirical distribution, we would just have these two terms, and now there are additional terms coming from the estimation of the beta. Okay, so I'm going to call this again my W, so I want to mimic this W by using a non-smooth bootstrap. And the idea is very similar to what we did in the non-parametric case. So I'm first going to center my residuals, although here in this context, it's not necessary to center if you have an intercept. So you can actually also work with the original residuals. Then I draw my bootstrap errors from that empirical distribution. I obtain responses. With these new bootstrap responses, or with the bootstrap errors, I obtain a new beta hat star. And with the new beta hat star, I obtain my bootstrap residuals. Okay, so exactly the same idea as in non-parametric regression. And again, we are interested in the behavior of this process, so which compares the empirical distribution of these bootstrap residuals with the empirical distribution of the original residuals in the real world. And we want to show that this converges to this process W. So here is really a summary, but I'm skipping the details. I'm not giving you the different terms in the decomposition as I did before, because it's really similar. So the end message is that we use again a result that existed already about the smooth residual bootstrap process. And that was actually shown by Hirakul and Lahiri, Suman Lahiri in 1994. So they used smoothing in this context of linear regression, which is a bit surprising because there is no smoothing at all. It's a linear regression model. But they introduced smoothing, because that's needed as a technical tool in the proofs. Yeah? So what we showed is that this smoothing is not necessary. You can simply take the non-smooth residual process. Okay, so that was the theory. Let's now see how it works in practice. So in the simulations, we did three things. We looked at bootstrap confidence bands for the error distribution. We looked at testing for a symmetric error distribution. And we looked at goodness of fit tests. So in the interest of time, I will probably only look at the first and the third point, and I will skip the second. So let's first look at these confidence bands. So suppose we want to construct a confidence band for the whole error distribution. And we will do that by using the non-smooth bootstrap and, of course, by using the smooth bootstrap to see how these two behave. And so a confidence band, one way to do that is to add and subtract the quantile of level 1 minus alpha of the distribution of the maximum of your process. And we then, of course, use smooth and non-smooth bootstrap to approximate that distribution. Yeah? Okay, so this is the setting we considered. So we took the non-parametric regression model with as regression function to x, a normal error, a uniform covariate. For the bandwidth, we took a very simple choice, which was a constant times n to the minus 0.3. Why 0.3? Because that bandwidth satisfies the regularity conditions that we used or that we needed in the theory. And for the constant, we took simply the standard error, the standard deviation of the covariate. So this bandwidth turned out to work well in practice. Of course, it might not be the best one, but it seemed to work for our purposes. So then, for the smooth bootstrap, we also have to choose the smoothing parameter. And there we used a cross-validation approach, which was developed by Jeff Racine and co-authors for smoothing a distribution function. Okay, so here are the coverages and the average width of the confidence bands for different sample sizes, and each time for the smooth and the non-smooth bootstrap. So what do we see? We see actually that for the smooth bootstrap, the coverage is usually too small, and it does not really improve when you go to larger sample sizes. For the non-smooth, it's a bit the opposite. The coverage is far too large, I would say, for small sample sizes. But fortunately, it gets better when you go to larger sample sizes. Of course, it's possible that the smoothing parameter that we are using for the smooth bootstrap is not the best one, but actually we don't really know how to choose it. And yeah, that's also an advantage of the non-smooth bootstrap. You don't have to choose it, so you make life easier. Okay, so that's for the coverage. Now, if we go to the average width, it's not surprising to see that the smooth bootstrap has is smaller, is less, is smaller. But that's because the coverage is also smaller, right? So that leads to smaller confidence bands. Okay. So let's now look. I will skip this second application and I go to the last one, which is about the goodness of fit tests. So here I want to test whether the regression function is a certain parametric regression function. So as I mentioned before, it has been shown that testing this null hypothesis is equivalent to testing whether the error distribution is equal to the distribution of this quantity here, y minus m theta 0 x, where theta 0 is the value of theta that minimizes this. Yeah? So, of course, from the left to the right, this is obvious, but you can also show that it's true from the right to the left. Okay, as test statistic, we are going to use the Kramer-von Mises distance, but you can also look at Kolmogorov-Smirnov. In the paper, we actually did both of them. So we know how to estimate this quantity here. This is the empirical distribution without smoothing. And here we are using the estimator under the null, which is based on the smoothed parametric regression function. So this is similar as what Herle and Mammon did in their paper. They also smoothed the parametric regression function in order to have the same bias for the two quantities that you compare. Okay. Now, of course, here in the context of hypothesis testing, you have to make sure that you bootstrap under the null hypothesis. Yeah? So you have to adapt the bootstrap procedure so that it's constructed under the null hypothesis. So we have to do the following slight adjustment. So we create these bootstrap errors as before, and then the bootstrap responses are constructed under the null hypothesis since we add here the regression function under the null hypothesis. Yeah? And then I think the rest of the procedure is quite standard. So we estimate the theta, the parameter, from the bootstrap data. From there, we get the bootstrap estimator under the null, and that we plug in our test statistic. And of course, for the smooth version, we do the same thing, but yeah, everywhere you have to add smoothing in these steps. Okay, then we looked at actually two cases. We looked at a case where the errors are normal. That's the first case. And then we also looked at the student T with 3 degrees of freedom. And actually, this second case is a case that does not fulfill the conditions of the asymptotic theory, because we require certain moments for the error distribution, and these conditions are not satisfied. So we want to see in which sense our procedure and the smooth procedures are sensitive to these conditions on the moments. Everything else is a bit similar as for the first simulation setting. Under the alternative, we consider this, so 2x plus some quadratic form. And so let's now look at the results. This is the result for the normal case. So each time you have Kramer von Mises for the smooth version first and then the non-smooth. A equals 0 corresponds to the level. And then these two correspond to power. Yeah. So what do we see regarding the level? We see that both bootstrap procedures lead to conservative results. Even if the sample size increases, it gets better, but it's still conservative. But the non-smooth bootstrap is more conservative than the smooth one. Yeah. For the power, we looked at the adjusted power, meaning that we look at the power when the level is exactly alpha. So we adjust the critical values so that we have exactly a level alpha test, yeah, in order to ease the comparison. And we see that if you do that adjustment, there is almost no difference between the smooth and the non-smooth. They give almost exactly the same power. Yeah. If you look now at the student T, the conclusions are a bit different regarding the level. So we see that for A equals 0, the smooth bootstrap is actually now a bit anti-conservative, especially for small sample sizes, whereas the non-smooth bootstrap is doing quite well. And again, after adjusting the power for getting the same level, we see that the powers are almost the same. So the conclusions for the power are the same, but for the level, there is a slight difference. Okay, I'm going to stop here. So as a conclusion, I think we can say that the smooth bootstrap is sometimes a bit anti-conservative, not always. In some cases it was, in others it was not. Whereas the non-smooth bootstrap is usually a bit conservative. Yeah? So if you prefer conservative tests, which is what we tend to prefer, then you would conclude that non-smooth bootstrap is maybe better. Yeah? And in addition, you don't have to choose that extra bandwidth parameter. Yeah? Okay, so here is a summary of what we did and some references. That's it.
Any comment with respect to the first part of the non-parametric case? There are all papers telling that for the estimation, the non-parametric regression, we have to use 2 different bandwidths. You use the same bandwidth for the estimation of M in the bootstrap and in the original data?
You are referring to the papers of Herle and Baumann,
yes,
and who else? Well,
Mammon.
Yes. So, but that's for the case where you are interested in bootstrapping the regression function itself. Here we want to bootstrap the residual distribution, and in that case it's not necessary. Yeah.
Okay.
Yeah, just to say that the problems are not completely unrelated. When you estimate a distribution function, you are also estimating an expected value. So that's also, and also when you're estimating the residual itself, you have to estimate the regression function first. So these problems are not completely unrelated.
No, they are of course not completely unrelated, but when it comes to the bootstrap, in the case where you want to bootstrap the regression function, it's really necessary to oversmooth. Whereas in this case, yeah, the asymptotics show that it's not necessary.
Okay, thank you, speaker. The third speaker for this session is Holger Dette.
Okay. Good. So thank you, Emanuele, for organizing this nice conference and all the organizers. Yeah. Anyway, so I keep my thanks very quick, but I'm very grateful to be here. So I'm talking about joint work with Stanislav Wolgoshev and Kevin Kokot. Stanislav Wolgoshev is a former postdoc. He's now professor in Toronto. And Kevin is a PhD student in my group. So it's a title, Relevant Hypothesis and Functional Time Series. Let me see if I can use this. So I give you some motivations, and we have some discussion about relevant hypothesis. Then I give you some very detailed arguments for one-sample problems. I even might give you some ideas and proofs. They are not so complicated as Ingrid's proof, so they are much easier. So you can do it with high school mathematics, so it's nice. Anyway, I'm cheating, but anyway. So then we talk about change point problems, and then I draw some conclusions. And everything I'm talking about is based on a preprint, which you can find on the archive. It's currently under revision. And maybe the references are here, so I hope to convince them it's good work. I'm very excited about that work. So this is typical functional data. I don't analyze this data. I just want to state the main problem. You have two locations, Sydney and Cape Otway in Australia. Alex we got this data from Alex Auer. He's always using this. And so you have several years, and you have the temperature of a year. This is scaled to the interval 0, 1, and then so every data point is a function, and you can define a mean function for each time series at each location, and then you try to compare the mean function. So basically, we have a two-sample problem with functional data. Yeah, and you want to test if these two mean functions are the same. And of course, they are not the same. You already see this from the data. But anyway, so it's just for motivations that we get up for the setup. So typically, we have two samples with two functional mean functions, and the typical question is if there exists a difference between the two mean temperature curves at the both locations. I denote the two temperature curves by the mean temperature curves by mu x and mu y. So, and we formulate it by putting a metric on some space, and then we just deformulate the null hypothesis that the distance between these two mean functions is 0, and the alternative is that's positive. Okay, and we can take, of course, any metric here, and mu x and mu y. I have already mentioned that these are the mean functions of two independent functional time series defined on the interval 0, 1. Okay, all right. I might want to pose a question. If we are really interested in this hypothesis, I don't think so, because we are not interested in small differences. In particular, it's very unlikely that these two mean functions at these two locations are precisely the same. So it's basically, we're testing a hypothesis we know it's not true. Okay, so it might be more reasonable to test if the mean functions do not differ substantially. Yeah? So that might be a more reasonable hypothesis. We do this hypothesis that they are exactly the same because we get the theory is simpler. That's the reason why we do it. But scientifically, I think it's not so reasonable. And it might be more reasonable to test the following hypothesis, verbally formulated, if there exists a scientifically relevant difference between the mean annual temperature curves at these two locations. So, and then you have to, of course, to define the scientifically relevant, but that's that's difficult, of course, because you have to talk to people outside of mathematics, so that's difficult. But Anyway, let's assume that we can do this, and I can give you examples, not in the functional context, functional data context, but I can give you many examples where it's very clear how to choose a threshold delta such that you can test the hypothesis that the distance between the two mean functions is less or equal than delta, and the alternative is that it's positive than delta. Okay, so, and there are very many areas where you can define this delta very in a good way. In functional data analysis, the applications are not so well developed that they have guidelines or something like that right now. But anyway, okay. So D is a suitable metric here as well. Mu x and mu y are the mean functions. Delta is a threshold, and this is what we consider as relevant. Okay. So I mentioned if you like the classical case, you just put delta equal to 0. Okay, that I call classical hypothesis, but I argue that you somehow should think about this very carefully, because philosophically you're testing a hypothesis which you know that it's not true. Even if you test two real, even if you do the t-test, it's very unlikely that the means are exactly the same. Anyway, okay. Interestingly, if you go for this setup, the metric matters, right? I mean, if two functions in one metric might be very close, but in other metrics they might be very different. So you have to think about the metric, which is also very interesting. So you have to think more. And of course, the choice of the threshold depends on delta and on the metric and on the concrete application. Okay, good. All right. So the metric matters. So we could do this one, yeah, and so we could do the submetric. Yeah, so we could do the submetrics. Then you go into Banach spaces. This is so difficult for this afternoon. It's a Saturday afternoon, so usually I watch soccer games during this time. So I don't do this one here. So I don't do the Banach space stuff. I do something different. I do what all people in functional data analysis usually do. They go to L2 methodology because it's simple. You work in Hilbert spaces, and Hilbert spaces have a nice structure, so we go this way. Okay? So we do Hilbert spaces. We took the L2 metric induced by this inner product here. The metric has the index 2. I just realized that at some places I forgot the index 2 and the norm, but it's always the L2 norm. Okay? All right. And then we have our elements are random elements in the L2 space. Okay. Before we now start, I want to make some general comments. If you have accepted, or you have to accept because you're sitting here, that we do this. Yeah, so, but if you do this, I want to mention that this is more challenging than testing the classical hypothesis. One reason is that under the null hypothesis, you usually cannot work on a common distributional assumption, because a null hypothesis is an infinite dimensional ball in the L2 space. So you don't have a common distributional assumption like stationarity or something else. So that's one point. Okay, so for example here, if you have this null hypothesis, and so the distributions completely coincide except of the mean function, you still have different mean functions. So it's more difficult. So, and as a consequence, you have to modify everything you know. So you have to modify everything you know. Even if you look at the classical t-testing problem, you have to modify this. Yeah. So in our context, we have to modify asymptotic theory. We have to modify bootstrap. If you want to do bootstrap, you cannot, because the null hypothesis is a huge class of distributions. And you also have to modify self-normalization, which I explain you a little later. And because it's so complicated, we will start with one sample problem where I can explain everything quite well, hopefully. I do my best, and everything is very transparent. So that's a one sample problem. We have a stationary time series in L2, and we have a mean function mu. We have a long run variance, call it Cx. Well, it's not working anyway, so we call this long run variance Cx. Everything depends on arguments st, so it's not completely trivial to define these expressions, but anyway, we believe that they exist. And now we want to test that the mean function does not deviate in a relevant way from 0. So we test if the mean function, the norm of the mean function is less than the threshold delta. And the alternative is it's larger than delta. Okay? And everybody knows how to do this. Yeah, I mean, everybody here in the audience basically everybody knows how to start, let's say it that way. Okay, we want to say something about the mean function. So we estimate the mean function by the sample mean, xn bar, and we just take the norm of the sample mean. Okay? As the L2 norm of the sample mean, and then we reject if this L2 norm of the sample mean is large. That's clear. So the only question that remains is how do we get critical values? Okay. All right. So that's the solution. Everybody knows this. This is the solution how to get critical values. And I explain you. So this is the squared L2 norm of the mean, and you can write it. Yeah, you can write it, if you subtract the mean, you can write it as a squared L2 norm of the mean, of the centered mean, plus 2 times an inner product of the centered mean times the mean function. It's just the binomial formula, okay? And if you know this one, and now if you look a little bit at books on reconvergence as Piotr's books, Piotr and Larios' book or something like that, then you can, under suitable assumptions, you can prove that's a mean function minus a mean, that's a sample mean function minus a true mean function times square root of n converges in L2 to a Gaussian process. So let's call it Z, okay, with some long-run covariance. So you need some technicals. I give you some conditions later, which I skip, but anyway. Okay, if you have this one, then you know the order of these two quantities. I think I do this on the next transparencies. You have this decomposition, you know the order of these two quantities. So if you multiply everything, if you multiply the first term with square root of n, it's basically of order 1 over square root of n, okay? If you multiply the second term here with square root of n, you can put it in the integral, and then you see basically by continuous mapping that it converges weakly to a standard normal distribution. Yeah, so it's quite easy. And all what you get there is it's not standard normal. It's a normal distribution with some variance. I call it tau square. It's not working. So in tau square is a long-run variance. So it's somehow an integral of this form. So it's quite easy to do. So if you basically, as soon as you have the weak convergence, it's just continuous mapping. Okay, so it's just continuous mapping. All right, and then you know what you to do. So you can put that together. So if you center the L2 norm of the sample mean, the squared L2 norm of the sample mean, by the squared L2 norm of the mean function, you get weak convergence, if you multiply with square root of n, to a normal distribution with this long-run variance. And here are assumptions which I skip because otherwise the expert find errors here in these assumptions. No, I'm kidding. I think they're okay. So basically you can prove a central limit theorem under certain assumptions, like M approximability or all these stuff which Piotr and all these people are doing. So you can prove this one, okay? And then you also know what to do, or no, maybe not, if you still don't know it, but anyway, you can define a test for the hypothesis that the mean function is L2 norm of the mean, the squared L2 norm of the mean function is less or equal than delta by rejecting if this expression on the left-hand side is larger than the unknown long-run variance times the 1 minus alpha quantile of the normal distribution. So it's very simple if you know the long-run variance. So it's very simple if you know the long-run variance. And you can prove, and I don't know if I have it on the transparencies, I deleted something. You can prove that the test is asymptotically consistent. It's consistent, it has asymptotic level alpha. I put this, so this is just a probability of rejection. And you have to be a little careful to understand that I put this really here because that you see because the null hypothesis is big. So you have two cases in the null hypothesis. One is if you somehow the true L2 norm is strictly smaller than the threshold. Okay, then it converges to 0. If it's exactly equal to the threshold, it converges to alpha. And of course, if you're on the alternative, always converges to 1. Okay? And the only problem that remains is estimating the long-run variance. That's the only point, or not estimating. So we don't know the long-run variance. Actually, you should not estimate. I advocate do not estimate it. So here's this first solution, what people would say, estimate tau. Here still have a good formula. You can try to estimate this. But I give you a short example here. I don't explain this formula. It's just I just give you a short example where I did just one simulation. We just generated a functional autoregressive model of order 1, and in this example, the long-run variance is given by this expression here, and this is basically the autoregressive parameter. And so that's basically the autoregressive parameter. That's all that you can have to take from this transparency. And what we now did is we just took, you can take any long-run variance estimator. You can, whatever you want. We didn't try all, but we tried many. And now you get a typical picture if you estimate the long-run variance. And what I show you on the next transparency, I show you the approximation of the nominal level if you are at the boundary of the null hypothesis. So it should be, at that point, it should be alpha, exactly equal to the nominal level. Okay? And that's what I show you here. And this is what's happening. So this is kappa, which somehow specifies a dependency. This is this line here is a level. And now I have to be careful. I cannot see it, actually. It's so bad. So the dashed line is the asymptotic level at the boundary, which should be 5%. So it's much too large. It depends really on the value of kappa, which you, of course, don't know. Yeah, so that's the point. And that always happens if you take now a different long-run variance with a different bandwidth, some other pictures happen. So it's not working. So it's, yeah. Here it's and here you have another one. This is, I think it's a boundary where both threshold and true L2 distance are equal to 0.5, and here they are both equal to 1.5. Anyway, interestingly also, if you would know the long-run variance exactly, it's also not working. So that's a solid curve here. So it's even worse. So even if you would know the long-run variance, it's not working. So it's worse. We have no explanation for this. Don't ask me for this, why it's not working. It's getting better. You see, it's getting better. So here it's worse than the estimation, but here it's getting better. So and if the sample size is increasing, it's getting better. Yeah. So, but anyway, so it's not good to know the long-run variance here in the setup. Anyway, so we have to do something. Second solution, bootstrap. Yeah, I don't talk about Bootstrap today. You can try to do it, but it's time series, and Bootstrap is also difficult in time series because then you have to maybe sample blocks or whatever. So and you have to also do some tuning parameters. So I don't want to do this one. My experience with this one in the other paper where we did the subnorm, Bootstrap is doing better than long-run variance estimation. But I still don't think it's the best way. So what I want to do now is I want to give you a non-standard self-normalization. It's non-standard because we consider these relevant hypotheses, so we don't consider classical hypotheses. So self-normalization is a very well-known concept in time series analysis if you consider classical hypotheses. But I want to do it for these relevant hypotheses. Okay? So that's what we're going to do. Okay, so that's what we do. And now it's getting a little more complicated. So far it was quite easy. So what I do now is I define a partial sum process indexed by an index lambda. So I just take the sample mean up to order lambda, n lambda, okay, basically. Okay, and I do this for every lambda. And of course, if I put lambda equal to 1, I get the sample mean. So the statistics that I have in mind is just the partial sum process evaluated at lambda equal 1, squared, and then integrated. So that's this one. And then I define a self-normalizing factor, which is defined here. So I don't have the time to explain why this is the right factor, but yeah, so I don't know if I have transparencies, but anyway, we'll see. I think I deleted them because of time. Anyway, so this is a self-normalizing factor. You basically do something similar. You take the integral with respect to every lambda of the squared partial sum process, integrate with respect to t. Then you take the integral with respect of this process evaluated at lambda equal 1 and multiply with lambda squared. You take the difference and square again. And then you integrate with respect to some measure. So I'm an honest guy. I tell you that you can take any measure here. If I would be a not honest guy, I would just take the Lebesgue measure. Yeah. So then you don't ask me how to choose the measure. Yeah. So later on you will ask me how to choose nu. But you can choose nu whatever you want. So I take a uniform distribution at 19 points or something like that. Yeah. Anyway, good. That's a normalizing factor. And then what you can prove, and that's a little more complicated, you can prove now the things that we had before, Tn hat minus the L2 norm of the true mean function times square root of n times square root of n times the normalizing factor converges as a vector to this quantity. The first one is just tau, which is the unknown long-run variance, times the Brownian bridge evaluated at the point 1. And the other one is some kind of functional of the Brownian motion multiplied with tau. Okay? And when you now see, if you divide both sides, then tau is canceling. So you get some kind of pivotal statistic here, which is somehow functional of a Brownian motion. Okay? Okay? And the variance does not depend, as the distribution does not depend on tau, but it depends on u. Okay, so you can choose new. I tried to find the best one because I'm an optimal design person, so what's the best new? But I was not able to find it. Yeah, so it's quite stable. Numerically, it's quite stable if you don't do crazy things. Yeah. Okay, all right. So now we are in business. We do the same thing as before. We just replace, in the decision rule, we just replace the quantize of the normal distribution by the quantize of the distribution of this pivotal statistics W. That's all what we do. Okay? Okay, and then we reject the null hypothesis whenever Tn hat is larger than the threshold plus normalizing factor times the quanti. And this function here with the triangles is the function that you get if you do the self-normalization. Yeah, so it keeps this level at the boundary. It's very stable. Yeah, let's say it that way. Okay? It's extremely stable. Okay. So it's stable. Okay. Anyway, you can prove this. But before I prove this, I have another note here. Okay, so it does not depend on the long-run variance. And the distribution depends on the measure nu. So for each measure, you get a different distribution. But I just gave you, because you can just simulate them, I personally would just take the first one, just a uniform distribution at 5 points or something like that. Yeah. So here are the quantize of the distribution. All right. Okay. And here's now a theorem which says that this is really an asymptotic, consistent, and level alpha test. Yeah. So it says basically has the same properties as before. If you are at the boundary at the hypothesis, you approximate the level alpha. If you are in the interior, you convert the level convert as a probability of rejection converge to 0, which is nice. You cannot do better. Of course, you're in the interior. You just want to need one point where you have alpha, right? Otherwise, you want to have it push it down to 0. And at the alternative, it converges to 1. Okay, that's the last line here. Anyway, okay. So that's my message here. I have another simulation. So that's basically the same thing as before. We have now a functional moving average model. Theta is a random operator, and these are somehow obtained by forming a sum of B-splines with normally distributed coefficients. Okay, we just took an example of the literature, and then we also have IID errors, which means where we just have eta j is epsilon j is equal to eta j. Okay, and I just want to show you the typical picture. So we test is that the hypothesis that the squared L2 norm is less or equal than 0.02. Okay, and this alternative is larger. And these are the typical pictures. You see at 0.02, you are pretty much at the level alpha in the interior of the hypothesis. So if the distance is strictly smaller, it's close to 0, and then it somehow approximates 1 depending on the sample size. So it's basically actually doing exactly what we have predicted. And now I briefly go to change point problems, then things getting more. We have many things in the papers, yeah. But I just briefly go to change point problems, and I go to a very simple one. We just have one change point, yeah. So at the beginning we have just a mean mu and some kind of error process, and after the change point we have mu plus delta, and the shift is then delta. Okay, and then we have all these assumptions to do the zero. It's not necessary to talk about that because I think the nice thing of this talk is the idea. So we test if the shift here, before and after the change point, is less or equal than a threshold. And what we do is, let's assume that we can estimate this change point. There are many estimators here. You have to be a little careful, but because it's functional data, but basically we found an estimator. And then what you do is you compare the mean before the estimated change point and the mean after the estimated change point. Basically, you're back in this two-sample problem. And then you reject the null hypothesis if the L2 norm of this expression is large. Okay, and the only thing what you have to do now is you have to take care of the self-normalization. Okay? So, what is this? No, it's okay. That's a self-normalization. So okay. So now we have to introduce another partial sum process that's getting more complicated. So you take a partial sum process for each theta, which you don't know, before the sample of all from 1 up to n theta, and then another partial sum process after that. Okay, and then you realize if you put in for theta the estimator, if you put in for lambda the 1, you get the test statistic, and then you know how to do self-normalization. Okay, and then you basically can use the same quantize of the distribution of the random variable W, which I've introduced. All right. And you can prove a similar theorem. This works as well, quite reasonable. Yeah, and I want to, I'm quite honest today, so I give you some simulation. I also give you a case where it's not working. Okay, I give you a case where it's not working to explain why it's not working. Okay, so I have a very simple case here. So first the mean function is 0. After that, it's a times t times 1 minus t. Okay? And I have some kinds of errors. Somehow I have independent errors. I think I don't know. I thought I also have other errors. No, maybe I just have independent errors which are functional. It's just a sum of B-spline functions with normal distributed random coefficients, independent. And we want to test the hypothesis that the L2 norm of the shift is basically a times t times 1 minus t, is less or equal than delta. So the L2 norm of the shift is a squared divided by 30. Okay, so I always think it's wrong, but it's a squared divided by 30. I put the two thresholds here. Now, the one is 0.1 squared divided by 30, and the other one is 0.3 squared divided by 30. And here are the results. So this is for the small threshold, and this is for the large threshold. I wouldn't say it's small, but anyway, it's larger. So you see here everything works very well. So at this point 0.3, the level is precisely alpha. Here it's not really working. We overestimate the probability of rejection, so it's too large. And the reason is that the threshold is very small. It's 0.1 squared divided by 30. So it's 0.0003. Yeah. So it's a very small threshold. And the reason, if you have this small threshold, you cannot, then you cannot estimate the change point precisely. So what you see here in the left part is a histogram of the estimated change points under the hypothesis that the deviation is exactly 0.003. Yeah, so you cannot estimate it precisely, and that somehow disturbs your level. If the threshold is a little larger, if it's 0.03 or something like that, you can estimate the threshold precisely, and then the test is working. So everything what I'm presenting here requires precise estimation of the threshold. That's what I want to say. I think it's so. I don't give you the data example. It's quite nice. It's from a civil engineer of the University of Bochum, but I don't give it to you. Anyway, some concluding remarks. So what I presented to you is I gave you some pivotal tests via self-normalization for relevant hypotheses. Here I was talking about relevant deviation in the mean. I did not talk about relevant deviation between two means, but that's basically the same as the mean. And I also talked about relevant change in the mean. But you can do this whenever you have L2 distances. So in the paper you find relevant differences between two covariance operators, and you find also relevant change points in the covariance operators. You find also results on that. And we're currently working on really challenging problems. We are interested in relevant changes between relevant differences between eigenfunctions or eigenvalues of two covariance operators. Or we're also interested in relevant deviation from separability. Yeah, Piotr was mentioning it quite recently. Yeah, and I want to emphasize, here I was just playing, so I still had a good formula for the long-run variance. I was just saying I was not able to estimate it. Maybe if you work very hard, but we really worked very hard to estimate it precisely. So if you work very hard, you may come up with a long-run variance. In these examples here in red, the formula for the long-run variance is so complicated that there is no chance to estimate that. For example, if you have the long-run variance of the corresponding statistic for the difference between the eigenfunctions depend on all eigenvalues of the covariance operator and on all eigenfunctions of the covariance operator. So there's no, and on the dependent structure of the time series. So I don't think that there's any way to estimate that. So you really have to rely on these concepts. And I think that's all I have to say. Thank you very much.
questions?
Of course, if you want to be pretty sure that the difference of your two functions is small, then you test the other way around. So
Exactly.
delta is the other way, which works in the same way.
Exactly. That's also another point. The problem is completely symmetric.
Yes, yes.
I actually deleted it from the transparency because I only have 25 minutes.
And of course,
Yeah.
and another thing, of course, you have asymptotic confidence intervals. Let's say. And
Yeah, as well.
This is the next point, because then maybe you need not testing, because you have your confidence interval and you make your decision.
No, that's
based
right.
on the confidence
I,
interval.
the reason why I always do this testing stuff is because all these problems are motivated by my work with the biostatisticians from Novartis. They don't do functional data, but they test these hypotheses. And in biostatistics, I don't know why they don't do confidence intervals, but they always do testing for equivalence, testing for relevant differences. Yes. And that's the reason why I'm staying with testing.
And the last point, so it is basically that you have asymptotic normality if you have weighted L2 statistics.
Something like that. Yeah, under the
and
alternative.
This is really still underestimated by many people.
Oh yeah,
at this
I know.
point.
Yeah, I know. Yeah.
So what you called as self-normalization essentially showed up what you call the classical case as the ratio statistics.
Yeah,
because in this case, essentially nothing depends on the long-run variance there. And I would say, okay, then people talk about self-normalization. It was related, okay, to the variance of the test statistics there when you are looking at the maximum there. And in this case, there was a problem, okay. So essentially, we were looking at a statistic which had at least asymptotically constant variance there.
Exactly.
And this is, I would say, okay, so it's not exactly like that one. So I would say, okay, sooner or later it will be confusing that in the scalar case that is considered like self-normalization and what you call self-normalization, those are not exactly the same thing. So in some sense, this is again some kind of a ratio statistics like that one.
Okay. Yeah.
Now this is just terminology because so later people get lost there. Yeah.
Okay.
I will say some of your formulas, okay, when you had this normal limit there, okay, those I think in the book what we wrote in Piotr Kokoschka, as the result, like how the test statistic is working under the alternative there.
Yeah, no, yeah.
So
that's what
the normality is essentially there. It's not even our result. It is coming from the 1950s.
No, it's quite old because when it's already for the grammar from Mises test or something like that.
So even the maximum, if you would like to do the same thing from the supremum norm, this will be again normally distributed there.
No, that's not normally distributed if you take the sup norm.
Yeah.
It's only normally distributed if the sup norm of the mean functions in a set of extreme points is a singleton.
Yes.
So no,
that's like that.
No, all these results, in the classical case, all these results are well known in the 60s and 70s.
Okay.
I completely agree.
Yeah.
So when you demonstrated that this long-run variance is not good, you used I noticed that you used an AR model in the simulations.
Oh, we used many models.
Yeah, and the AR model somehow, when the dependence gets stronger, so the size was not kept actually anymore.
Exactly.
But afterwards you used an MA model in the self-normalized case. Was this on purpose, or I mean, is it also like the same?
This was. I don't know. I don't know if it was. I just asked Kevin run a simulation because we had another context on open-end procedures. We have such a bad experience with long-run variance estimation. It was never working. So I just said, just take something. The reason why we took the AR1 model, I think, is because then we had a formula for the tau square. I think that was the only reason why we took the long-run, why we took this model. Yeah, if I remember correctly. And we also took different basis functions. Here we took, I don't know where it is, we took, where are these pictures? We took the Fourier basis, and later on we took B-splines. And the only reason why we took the Fourier basis is because I wanted this formula. I wanted an explicit formula for tau square, independence of the parameter. That was the only reason. So there was not, maybe it's working better for the MA one. I don't think so. Yeah, maybe a little bit, I don't think so.
Speaker is Thomas Verdebaut.
Okay, thank you very much. So, this one, yeah, okay. Okay, so I would like also to thank the organizer for inviting me, giving this talk here. It's really great. Okay, so what is the title of this thing? This is various results on uniformity test for directional data. So this is a joint. I actually will present two different works or three different works. These are joint works, and I will cite my co-authors throughout the talk. And this will be related to the subject already tackled by Eduardo this morning. So this is related to so-called directional data, so data that are actually directions, so you do not observe the magnitude of the observations, only their direction. And you want to test the null hypothesis that your sample comes from a data generating process, which is very simple, which is the uniform distribution on this circle, sphere, or hypersphere. Okay? So, I will provide an introduction first. And then you see you have then two distinct parts in this talk. One part which is related to high-dimensional results, and one part which is related to, let's say, a bigger class of tests, but for finite dimensional sample spaces. Okay, so for the circle and the sphere only. And I will at the end conclude with some work in progress. Okay, some future research. Okay, so then I will skip this. I want you to have a coffee. So directional data applied in many different things. Okay, and so we have U1, UN, we have a data set, and those points U1, UN, their IID on this sphere, and the problem we look at is the problem of testing that this P, this distribution P, is actually the uniform distribution. And of course, everything in this problem is driven by the alternative. Okay, you will see that we will actually consider different certain types of alternatives. But one type of alternatives you could imagine easily, probably the most standard or the most classical alternative, is an alternative under which you so this is the uniform case, okay? And then there you select a direction, okay? Take the North Pole here, and you pull the probability mass along this North Pole, okay? So you charge so the probability mass is growing around this North Pole. And in this parametric model, you can do that using this kappa parameter. This kappa parameter is really like a scale parameter. So the theta parameter in the density there is the location parameter. And this kappa is like a scale or a concentration. This is the parameter that will give you actually the probability mass around this North Pole. Okay? And when this kappa is equal to 0, then you are back to the uniform. Okay? So if you look at, so this is a particular type of alternative, okay? And if you think about how to test this type of alternative, how to detect this type of alternative, certainly a good way to do that is to simply to simply consider the sample average. We all like the sample average, and we are convinced that taking the sample average there, you clearly see that the expectation of the data generating process there is moving. The expectation of a uniform vector is of course 0. By pulling this mass, you are changing this expectation, and you can feel that using this sample average is a good idea. Okay? It's a good idea, yes, if you take as an alternative this parametric model there, the test that rejects for a large value of the L2 norm of the sample average of those data points, which is called the Rayleigh test, is actually the likelihood ratio test. Okay? And this test, I will study it in the first part of this talk, in the second part, but I will also show you that this actually was already shown by Eduardo this morning. This test belongs to a large class of tests, which is called the class of Sobolev test, considered this morning by Eduardo. Okay? So if you think about different types of alternatives, and you have many types of alternatives, but if you think about something that will not only charge the North Pole, but will also charge the South Pole, that is, you symmetrically charge the North and the South Pole, then for this kind of thing, actually, a good test will not use the sample average because the expectation doesn't move. If you charge symmetrically those two poles, the expectation is still 0. But the optimal test, let's say, a test that detects nicely those alternatives is the test based on this sample covariance. Okay? So this test is like a test, if you think about the Gaussian case, this is like a test for the sphericity of the covariance matrix, and the alternative is, in an alternative of the form, you just consider a spiked covariance where you spiked into some direction there. Okay? So, this is another type of alternative, and this is another test. Okay? Good. So, yes. If you, of course, a particular case of those stuff, of this setup is what we call the circular setup. So if you are in the circular case, of course, everything is driven by a random angle in this case, okay? So that this Rayleigh test, you can actually rewrite it like that, and you see that this Rayleigh test only depends on the first trigonometric moment, okay? You only consider cosines and sines of the observations there. Okay? And my point is that this Rayleigh test belongs to this larger class of tests, which was called this morning the Sobolev class of tests. And this Sobolev class of tests is a test based on statistics of the form. The statistic there is just taking care of all the trigonometric moments. Okay? So not only cos of theta I, but cos of k theta I, and you take within this sum any k. Okay? So, of course, so you have coefficients vk squared there. Of course, if you take v1 equal to 1 and vk equal to 0 for k larger than 2, you come back to the Rayleigh test. So the Rayleigh test belongs to this class for particular choices of this vk. Okay. The Bingham test there also belongs to this class. Okay. Good. Okay. So a way at least I like to interpret this kind of test. You can, in a sense, interpret it geometrically, because here what you have there are simply those trigonometric moments or those trigonometric functions, and we know that those trigonometric functions are actually providing a basis of L2. Okay, so you can see this test as like that. You simply take your it's a pity. You take your observation on the circle, and you send this observation on the circle onto a subspace of L2, which is spanned by the trigonometric function cosine k theta sine k theta. Okay? And if you do it like that, that is, you take your observation on the circle and you send it to this functional space, you can rewrite this statistic like that by using an inner product into this L2 space. Okay? This is a way to rewrite this thing. So, rewriting this like that, the statistic like that, you can actually easily extend this way of thinking to the sphere, that is the sphere of the hypersphere, to larger dimensions. And what you have to do is simply to have in your hands an orthonormal basis of L2 of the hypersphere, the space of integrable function with respect to a measure, this is the classical surface area measure there, on the hypersphere. And a way to obtain such an orthonormal basis is to simply take the eigenfunctions associated with the Laplace operator on the sphere, and actually this provides those spherical harmonic things, and you can see it, you can just rewrite a Sobolev test like that. Okay? So, for instance, if you take the spherical case, that is, you take p equal to 3 there, okay, what is the shape of a Sobolev test on S2? It involves actually Legendre polynomial. So you see that you have there Legendre polynomials of order k that is involved in this quantity. And indeed, if you take only the P1 thing, you get back to the first moment and the Rayleigh thing. If you take only the second moment, you are back to this Bingham statistic. Okay? Good. So this was the introduction, and then I will move to those two parts. In the second part, I will only talk about this Rayleigh simple thing, really simple thing. And then I will move to some new results on Sobolev test. Okay? So the aim of this first part was to show how this Rayleigh test actually behaves in the high-dimensional setup. I mean, do we keep asymptotic optimality properties for this guy? Within which class of test? What is the rate at which? What is this choice of kappa n? What is the sequence kappa n which will be such that in the high-dimensional case this Rayleigh test will detect something? Okay. And so what we did is basically derive some asymptotic results for this Rayleigh test, under some alternatives. So the alternatives are exactly of the form, I mean, a particular case is this one, okay, the exponential of the scalar product between u and theta there. This function f, you replace this function f by the exponential, and you have this von Mises model, but we keep it semi-parametric by putting a f there, okay? So we assume we want to say something about the asymptotic behavior of this Rayleigh test under alternatives like that, okay? Okay, so f of kappa n. Great. So f is monotically increasing. We can really, theta there is really the mode of the density, okay? And we have also, we have to identify the couple f kappa n, so there is some restriction on f which identifies properly this kappa n. Okay? Great. So the first result is a result which is related to contiguity. What is the contiguity? The contiguity, that is, what we have in mind is, can we find a rate for kappa n? I mean, the classical rate, the classical contiguity rate in standard problems in the univariate case, or even if the dimension is fixed, is this 1 divided by square root of n rate. That is the rate at which a good test will start to detect the alternatives. You will have non-trivial power there. If the rate is below this contiguity rate, the test will not detect the alternative simply, and the test will be consistent if the rate is above this contiguity rate. Okay? So the question is, what is the contiguity rate? And this is just a matter of comparing asymptotically those two sequences of probability measures. I mean, the uniform and the one indexed by f and kappa n. And what we found is that if you take kappa n to be of the order square root of Pn divided by n, I forgot to mention that this is a joint work with Christine Cutting and Devi Panaven, this part. So if you take a kappa n like that, okay, then you have contiguity. And this result is what we call the universal result because it doesn't require anything on Pn. Okay, Pn can go to infinity quicker than n, or I mean everything is permitted there. I mean no restriction on the way Pn goes to infinity with respect to n. Okay, and you see that if P is fixed, you are back to, I mean, if Pn is simply P, it is fixed, it's not diverging to infinity, you are back to this classical 1 divided by square root of n contiguity rate. Okay? So far so good. So the question is, of course, once you get this contiguity rate, the next question is, does the Rayleigh test detect those alternatives? This would be natural. I mean, you have a test which is supposedly optimal against this class of alternative. What is the asymptotic behavior of this Rayleigh test under these contiguous alternatives? Okay. So to do that, to keep studying this thing, we derived what we call the local asymptotic normality property. That is, you simply look at the log likelihood ratio of the two likelihoods. Okay. And what we obtained is that this model is LAN in the sense that you have this typical decomposition and this typical development, this typical asymptotic development, with a linear term there, a delta, which is random and which is asymptotically normal, with mean 0 and variance gamma f. This delta thing is just the scalar product between the inner product between the theta n, okay, the theta n which is in this likelihood or within this measure there, and the sample average. Okay, good. So once you have that, once you have this kind of result, you can actually think like that. You have this. I mean, this asymptotic result. This asymptotic result also entails that actually optimal inference within this setup should be based on this what we call central sequence delta. There, I mean, on this object delta theta and f. And so you could think that. So the thing is that, of course, we don't want to specify theta n. Specify theta n under the alternative is kind of cheating. You don't like that, okay? But if you specify theta n, what you get is that this test based on the central sequence is locally asymptotically most powerful, okay, for any f, okay, at asymptotic level alpha. So you expect that simply replacing this theta n by the sample mean, okay, that is estimating this theta n by this sample average, standardized by the norm, something which belongs to the unit sphere, replacing this theta n by theta hat like that will provide you a good test, okay? And if you do that, you simply get Rayleigh, because you are back to this norm to the square norm of the sample average. So this is the first idea you have, okay? You replace this theta hat n by theta hat, and then you ask yourself, then Rayleigh should be locally and asymptotically optimal. And actually, it is not the case. It is not the case, and we can actually show that this Rayleigh test will detect alternatives that are not at this rate there, okay, square root of Pn divided by n, but alternatives that are of the order Pn to the power 3 divided by 4 divided by square root of n, okay? So actually, this Rayleigh test is not only this is not that it is not optimal against those alternatives, this is simply that it does not detect them. I mean, it is blind against those alternatives, okay? And actually, so you have a test there, which is an oracle test. We call it an oracle test because you have to specify the theta n there, okay, which is kind of cheating. The Rayleigh test doesn't show any power against those contiguous alternatives. And actually, then you start thinking, okay, well I'm maybe missing something. I don't think we are missing something. The point is that, of course, the fact that you specify this theta n under an alternative is really important in this high-dimensional case. And the price you pay, I mean, you will pay. I mean, it will be costly to replace this theta n by an estimator because this theta n has a dimension that grows to infinity with n. So this is actually costly, and it is so costly that you pay the price with a rate. Okay, not only with a change in the power, but with a rate in this high-dimensional setup. Okay, so questions. Of course, what we obtained until there is for this theta n specified problem, but you don't want to specify theta n. Okay. The question is, can a test perform as well as the oracle test for the unspecified theta problem? So you want now to look at the unspecified theta problem. If not, can a test see the alternative of this rate? If not, can a test see alternatives that are more severe than the alternatives that are detected by this Rayleigh test? And if not, would Rayleigh be not only rate optimal, but even most powerful? Okay? And what we did there is to simply restrict ourselves to the class of rotation invariant test, okay? If you want to get rid of this specified theta n alternative, one way to do this is, in a sense, to restrict to those rotation invariant alternatives, so that you will kill these reasons doing that. Okay, and so rotation invariant. So you consider a group of rotations. Okay, the group of rotations, and of course the testing problem there is invariant with respect to rotation. You can rotate. The null hypothesis, you can rotate the alternative, you still have something which is under the alternative. And of course, it is more or less natural to consider rotation invariance because you don't want you want the decision to depend only on the distance between, only the norm of, the direction theta should not play a role there. Okay? Great. So invariant tests. What are invariant tests? If you want to consider tests that are invariant with respect to rotations, those tests they will have to be measurable with respect to what we call a maximal invariant. Okay? So what you should do now, if you want to construct optimal invariant test, is to look at the image of the model. You should look at the distribution of the maximal invariant. Okay, this is one way to do. Another way to do is simply to, in a sense, project your likelihood onto this. What you do is you take you take, let's say, invariant version of those likelihoods. This is equivalent to look at the distribution of the maximal invariant, or to do that. Okay, you just integrate with respect to the group of rotations your likelihood, and you get what we call here the invariant likelihood. Okay, so you simply take into account here. This is just so you integrate your classical likelihood with respect to this group of rotation, and this thing there is the R measure. Okay, there is a result by Morera saying that this is 5 minutes. No. Yes. 5 minutes. Okay. I'm in a bad shape. 5 minutes. Okay. So what we did is simply to study the asymptotic of this thing. Okay, the invariant likelihood, and we get again a line result. But a line result which involves now this rate, which is actually detected by this Rayleigh test. And we show that the Rayleigh test is actually most powerful, locally and asymptotically most powerful invariant. That is, if you restrict yourself to tests that are invariant, that is, you integrate with respect to this group of rotation your likelihood, then the contiguity rate for this resulting likelihood is actually this Pn to the power 3 divided by 4 divided by root of n rate. Okay? Okay, so we could answer those questions. No, yes, I skipped this. Simulations. Basically, everything is okay. You have curves, empirical versus theoretical. Everything is okay. It works perfectly. Quickly. Sobolev. So I go back now. This was Rayleigh, and Rayleigh is just a particular case of this class. This is a particular Sobolev test. And what you have on those Sobolev tests is you have the thing. I will do it really quickly. Provided that those coefficients vk square, okay, are summable, okay, you can easily get the asymptotic distribution of this quantity. This is just an infinite sum of weighted chi-square random variables. Okay. Of course, you can choose. Of course, these VK things they are driven by the alternative you want to detect. Okay, if you want to detect the unimodal alternative, you take Rayleigh. If you only want to detect the bimodal alternatives, you take Bingham. Okay, but then you can take VK as you wish. And it is well known that if you take a sequence VK square that slowly decreases to 0, okay, through simulations, people could show that what you do is you detect well what we will call here multimodal alternatives. Things like mixtures of von Mises distribution with a lot of locations for the peaks. Okay. So what we did here is simply to replace this. So we tried to obtain the asymptotic distribution. So the asymptotic distribution of this thing, replacing those VKs by 1. That is, it is not a sequence like that. Okay. And replacing this infinity you have here simply by a sequence that depends on n. Okay, and we simply let this kn goes to infinity with n. Okay, and what we got is the limiting distribution, which is here. So this is a joint work with Simos and Srinivas, which are probably in this room. What we got is the limiting. So we got that provided that you standardize properly this quantity. If you let kn go to infinity, but not too fast, that is, this kn must be little o of n square as n goes to infinity. This thing is standard Gaussian asymptotically. And of course, the resulting test, we show through simulation that the result, this is just a picture to say that it works. I mean, if n is larger than m, it is well. Everything is okay. The test is doing really well against multimodal alternatives, but this is expected because the weights are really big there. Okay. And we provided in the paper an extension to the spherical case. I mean, the thing involving those Legendre polynomials. But this kn, you see that this kn is not exactly. So this was for the circle only. So this was for the circular case. This is for the spherical case. And my guess, I don't have anything for the hyperspherical case, but my guess is that this thing will depend on the dimension of the subspace of, the dimension of the subspaces of the eigenfunctions in this L2 space. Okay, the dimension is moving. I mean, when the dimension of the manifold increase, this you will pay a price because of this. Okay. So I've just quickly finished by some work in progress. So the next step, these are results that are only obtained under the null hypothesis, and we would like to say something about the power of those tests. I mean, of those Sobolev tests. And actually, this last slide, this will be a joint work with Eduardo and Devi at ULB, Eduardo in Madrid. And with this last slide, I just want to try to be invited next time. Okay. We got something which was, in my opinion, surprising. I mean, when you think about it, it's not so surprising. But so this Rayleigh test is based on the sample average. Okay, the Bingham test is based on the sample covariance. Okay, and we are used to this orthogonality between sample average and sample covariance in this Gaussian world, meaning that if you take alternatives on the mean, the sample covariance will not detect those alternatives because it is invariant with respect to translations. And if you take alternatives for the covariance matrix, the classical Hotelling test will not detect those alternatives. Those things are orthogonal. Okay, so you could say, okay, for any kappa n there, this test will not detect multimodal alternative. That is the functions f such that it is not true. It is not true. No, and I have a proof that actually this Bingham test, based on the sample covariance, actually detects those unimodal alternatives, okay, but at a rate which is not n-1/2, at a rate which is n-1/4, provided that the second derivative of f at 0 is not 0. And I stop there. More next time on that. The references. Thank you. Coffee. Nobody. References. Thank you.